All right, class, welcome back. Hope that you were able to watch the videos from last week as well as the recording of the Friday Q&A. So what I figured I'd do is start off with, one of these problems that we left off. We talked quite a bit about these on Friday, but these were the types of problems that we were doing at the end of the last video lecture. So let's take a look again. Remember, we need to simplify these radicals. We need to satisfy the conditions of a simplified radical, which means none of these exponents could be greater than or equal to this index. So the way that we kind of showed how to do this last time was to split this up into the cube root of negative 27, and then the cube root of y to the 7th, the cube root of x to the 5th, and then the cube root of z to the 6th. And this one is pretty straightforward because 27 is a perfect cube, and it doesn't matter that this is negative because our index is an odd number. So we're able to take this cube root of negative 27 without any issues. We're not going to run into that problem of like it being a non-real number or something like that. So this is going to be negative 3, and of course there's not going to be anything left inside the radical because this is a perfect cube. And then remember, we talked about how these behave like old school long division, where you have how many times 3 goes into 7 as a whole number, and then you have some remaining value. So the way that we showed this on Friday was to think of this as 3 goes into 7 2 whole times, so the y squared comes out of the radical, and then there's a remainder of y to the first power, a remainder of 1. You don't have to put that 1 there, but I'm just showing you that this is 3 goes into 7 2 whole times with a remainder of 1. 3 goes into 5 1 whole time with a remainder of 2 this time. So again, 3 goes into 5 1 whole time with a remainder of 2. And then last but not least, 6 is divisible by 3. So this is just going to be z squared. And now that we have done the hard part, all we have to do is take stock of what's on the outside. So there's a negative 3, a y squared, an x, and a z squared, all on the outside because the radical is no longer there, and only a y and a x squared remaining on the inside of that radical. And that's how you simplify these radicals with the path of least resistance, in my opinion. Okay, as far as like satisfying the condition of the exponent not being greater than or equal to the index. Obviously, there's going to be other problems where we're going to have to simplify even more, but for now, this is what we have. So we've done our job in simplifying this radical. All right, so this doesn't violate that condition of the exponent being larger or equal to the index, but it does violate the condition that they have a GCF that is not 1. And one of the things that you can think about is if you were to write this in exponential form, remember this is your numerator, 3, this is your denominator, 12, and you would never leave this as 3 over 12. You would simplify this to be 1/4. So that makes perfect sense as to why this radical simplifies to be, again, a 4 on the outside and a 2 to the first power on the inside, because you can just sort of factor out that common factor of 3, or you can divide the common factor of 3, however you want to think about it. This ends up being now the 4th root of 2 to the first power. And the same sort of thing is happening here. Again, if you were to write this as an exponential form, you would have 2/6, which you would never leave that as a simplified fraction. This would simplify to be 1/3, which makes sense as to why you now have the cubed root of t as your final answer. All right, so these are pretty straightforward. These are pretty, embraceable and from a student perspective, because all you're doing is really simplifying the fraction. And anybody in a college algebra class should be able to do that with little or no struggle. All right, so that's exactly what's going on here. They're just showing you that you can sort of take out this common factor of k. If you have this k times n and this k times m, you see here that you just have an n here and an m there because they have divided out that common k that both of those had. So we just followed that quick guideline, even though we didn't know that it existed yet, because it's pretty straightforward to do. All right, so this becomes a little bit more challenging because, again, our indexes are not the same. And one of the common errors that students make here is, again, they think that they can do this by just saying, all right, well, this is just going to be, 5 times 4 is 20, so it's going to be the cube root of 20. And they just ignore the fact that this is not the cube root. This is the square root. And remember, in order to multiply these radicands, the indices have to be the same. And currently this is a 2. Remember, it's not a 1, it's a 2, and this is a 3. So the only way that we can get them to be the same is to use the least common multiple, the LCM, and the LCM is 6. So we want these both to be the sixth root for both of these. And the way that you do that is you have to raise this to the power of 3. So this is going to be 5 to the third power because, again, you had to multiply 2 times 3, so you have to multiply 1 times 3 as well. And that's just going to be 3. Over here, you don't have to multiply by 3. You do have to multiply this 3 by 2 to get 6. Remember, this 3 is turning into a 6. We have to multiply it by 2, multiply it by 2. Again, you're not multiplying 4 times 2. You are raising it to the power of 2. So this is 4 to the second power because, again, it's currently 1, 4 to the first power times 2, and which is going to give you 4 squared. And now that you have this, you should be able to say that this is going to be the sixth root of 5 to the third times 4 squared, which is 125 times 16. You can figure out what that value is. It doesn't really matter. Okay? But that's the idea behind simplifying these. Remember, you cannot multiply those radicands unless the indices are the same. So just make them the same if they're not, and then rock and roll from there. All right, so let's talk about everybody's favorite memory from geometry class, the Pythagorean theorem, a squared plus b squared equals c squared. Most students have some vague recollection of this a squared plus b squared equals c squared. Even if they don't remember exactly what to do with it, they just remember that alphabet soup and squaring it. And as soon as they hear it, they go, oh, yeah, I remember that at some point. Again, even if they don't know what to do with it, they still remember this pretty famous theorem. All right, so again, a squared plus b squared equals c squared. And again, the a and the b are the legs of this right triangle, and the c is the hypotenuse. The c is always the longest side of the right triangle, and it is always the side opposite the right angle. There's lots of other, theorems and postulates out there that talk about why this is the longest side, and of course, it's because it's opposite the largest angle, but we don't really care about that. We just need to identify our A, our B, and our C, so that way we can plug them into the formula in the correct place, okay? So this one's pretty straightforward because they kind of told us that we're finding C here. Generally, when you're solving these Pythagorean theorem problems, you're not given A, B, C. There's just like a question mark here. So you have to recognize that this is, in fact, the C. So that is what's going to go all by itself on the right-hand side of that equation. So you have 14 squared plus 8 squared equals C squared. And then this is going to be 64. This is going to be 196 is equal to C squared. This will be 260 is equal to C squared. And now we're playing the game of, well, we can't leave this because we don't want to know what C squared is. We want to know what C is. So the way that we figure out what this unknown length is, this side length C, we have to take the square root of both sides of this equation, and that will cancel out. Remember, this is the square root, it cancels out this square. And remember, it's the absolute value of c is what we're looking for, so we are caring about the positive version of this. So this is going to be c is equal to the square root of 260. Now, I'm willing to bet that there's probably some perfect square factor of 260 sort of lurking in the background here. So we can kind of look at this and say, all right, well, we have 260. Are there any perfect square factors? So you can test it. You can divide it by 4 and see if it's divisible. You can divide it by 9 and see if it's divisible, and just kind of play it out that way. So I know that 4 divides evenly into 260. So we can break this up so that it is the square root of 4 times the square root of 65. And the square root of 4 is 2. And the square root of 65 is just the square root of 65. And we can test to see if there are any perfect square factors of 65, but I'm pretty sure that there are not, since the only factors of 65 that are jumping off the top of my head are 5 and 13, which are both prime numbers. So there's no way in heck they're going to be perfect squares if they are prime numbers. So this is your simplified answer. Please, no decimals. That is the answer to this problem. I know it doesn't feel like it's a satisfying enough solution to this, but it is the length that we care about, okay? And let's go ahead and do this one. So this is, again, looks like they gave us a is 4, so a squared plus b squared is equal to c squared. So that's going to be 16 plus b squared equals 36. And now we're just banging out a little bit of algebra. So that's going to be b squared equals 20. And again, we don't care what b squared is. We want to know what b is. So the only way to do that is to take the square root of both sides. So we get b is equal to, and we have to do that whole business of finding the perfect square factor, which once again, it's 4. So this will be 4 times 5 is 20. So b is equal to 2 radical 5. And that is all she wrote for Pythagorean theorem. And I hope that that brings back fond memories of your high school geometry class, whenever that was. Okay. All right. The next order of business is this distance formula. And I'm not really going to focus too much on this, because if you are clever and you had a decent enough geometry teacher back in the day, they would have told you that this like nasty alphabet soup that's going on here is Pythagorean theorem. This distance formula is Pythagorean theorem with respect to the coordinate plane. And some of you are like, well, how could that be? It doesn't make any sense. Well, I'll kind of show you like how it was derived, and then we probably won't do one of these examples just because it's just plug and chug. And again, it's Pythagorean theorem. So, you know, you have this c squared is equal to a squared plus b squared, right? Again, I just wrote it in a different order, but that's okay. And remember, we don't want to know what c squared is. We want to figure out what this value is, right? I could easily change this to a d if I wanted to, right? Because it doesn't matter what that letter is. It's just some third unknown. So I'm just changing this from a c to a d because, again, it doesn't matter what it is. And again, if I didn't want to know what d squared was, which I don't want to know, I want to figure out what the value of d is, I would have to take the square root of both sides of the equation. And that's going to give me d over here, and it's going to give me the square root of some value a, which I'm supposed to square it, and then some value b, which I'm supposed to square that. Well, this is a number here. This x2 minus x1 is a value. I have no idea what that value is, so maybe I will call this value a. And then y2 minus y1 is also some value. Again, I have no idea what that value is, so perhaps I will call it b. And now you can see that this is d is equal to the square root of a squared plus b squared, which is exactly what I have over here. So yeah, this crazy looking formula that nobody seems to remember correctly is Pythagorean theorem. So if you can remember Pythagorean theorem, just go ahead and create the right triangle on the coordinate plane, and you'll get the answer, hopefully. All right. So again, I'm not going to focus on these just because it's just plug and chug. So let's move on. So 7.4, adding and subtracting radical expressions. So once again, adding and subtracting is a huge pain when it comes to algebra. super restrictive. You know, when we added, subtracted fractions, we needed a common denominator. So when we added, subtracted those rational expressions, we needed a common denominator. So the sort of the same idea is happening here, except we're not going to have a radical expression with the denominator, at least not yet. But it's still restrictive. So we're still going to have to do something to be able to add or subtract them within the problem. So in order to add or subtract these radical expressions, you must have the same index, so same index, and the same radicand. So if you don't have the same index and the same radicand, you cannot combine them, all right? You will not 100% not be able to combine if you do not have the same index and the same radicand. Just let it ride and move on with the problem, okay? So over here, we do have the same index. You see that this is a 2, the square root. This is a 5 and this is a 5, so it does have the same index and the same radicand. So we are going to be able to combine these so that it is going to be 3 plus 7, which is 10, and it's going to be the square root of 5. So if we have the same index and the same radicand, that index and radicand is not going to change, just like the common denominator. If you had the common denominator, it didn't change, right? It stayed the same. So it's not going to change here. And the only thing that is going to change is the coefficient. So this is still known as the coefficient of the radical, this 3 and this 7. They're still the coefficient of the radical, not the coefficient of the variable, but the coefficient of the radical. So you can sort of see like this parallel here, hopefully, that if you had 3x, again, you have some value here. The square root of 5 is a value, it's a number, right? I don't know what that number is exactly. It's the square root of 5. And this square root of 5 is the exact same thing. Again, I don't know what that number is, so maybe I'll just call it x. So this is going to be plus 7x, right? So 3 times some number, 7 times some number is going to be 10 times some number. Well, that some number just happens to be the square root of 5. So you can hopefully see the parallels that's going on between, you know, if this were an x versus if this were, you know, the square root of 5, which it is here. All right. So let's take a look at these. So you can see pretty quickly that this is the square root of 11 and this is the square root of 11. Hopefully you see that there's a 1 there, even if there's obviously physically not 1 there, except I just put it there. So you have 2 radical 11 minus 1 radical 11 is going to be 1 radical 11. So I'm going to leave that right there. And then when we peep over here on the third problem over here, you see that you have the square root of 44, which makes me think that we do not have the same radicand. But the problem is this can be simplified. This has a perfect square factor of 4. So this is going to be 3 times the square root of 4 times the square root of 11. And we know that the square root of 4 is 2. So this is going to be 3 times 2 times the square root of 11. And we know that 3 times 2 is 6. So this is going to be 6 times the square root of 11. So this whole piece over here became 6 radical 11. Well, remember, we're adding this to this existing radical 11. And now you can hopefully see that you're going to just combine these to get 7 radical 11s. You have 1 radical 11 plus 6 radical 11s will be 7 radical 11s. All right. So again, same index, same radicand. And then if you don't have it, then don't touch them. Don't combine them. Right? It'd be like 2x plus 7y. What's 2x plus 7y? It's 2x plus 7y. You cannot combine them because the x and y aren't the same. So the same sort of thing is going to happen when you're adding and subtracting these radical expressions. It's not the same index and same radicand. Move on with the problem. All right, so let's take a look at this guy. Again, you can see here that they're just saying that y is greater than 0, so that way you don't have to stress out about taking the square root of a negative number and saying that it's going to be non-real or something like that. So let's go ahead and do this. So these y's are cool because they have exponents of 1, and that is satisfying the conditions of a simplified radical as far as the y's are concerned. It's these numbers that are in here that are problematic for us. So this is going to be 5. And again, when we break this down, there's a perfect square factor there. That's going to be radical 4 times radical 3. And then, I'll leave the y underneath there because it's not going to bother me. Plus 6 radical 25 is the perfect square factor times 3y. Because again, that y is not going to bother anyway. When you take the square root of 4, you get 2. 2 times 5 is 10. So this is 10 square roots of 3y. When you take the square root of 25, you get 5. 6 times 5 is 30. So you get 30 and then 3y. And finally, we can add these together because we now have the same index and the same radicand. So this is 40 square roots of 3y, and we have successfully done this problem. So let's take a look at D real fast. Again, you have the square root of 5 here, and you have the square root of 10 there. And no matter how hard you try and get this 5 to be a 5 in here, it ain't going to happen. So just chalk this one up as a loss to the fact that you cannot simplify this. It is as simplified as it's going to get because there is no way to get this square root of 5 to be the same as this square root of 10. You can't factor out the square root of 2 in there because you still have the square root of 2 that you're multiplying there. All right, so it's not going to do what you need it to do. Unless you could take a perfect square factor out to get a square root of 5, it's going to be a loss. All right, so just move on to the next problem. All right, so let's just knock out one of these. It doesn't really matter which one. Maybe we'll do this one. So this is not satisfying the conditions of a simplified radical. Number one, these exponents are too big. So if we were to do the thing that we need to do, which is to bring them back down to earth here, 3 goes into 4 once, and you have a remainder of 1. So you have a p that's still inside here. So I am just kind of breaking this up and doing the job that I need to do all at once. So again, 3 goes into 7 twice. So q to the 2nd power with a remainder of 1. So pq inside there. The cube root of 64 is going to be 4. And nothing is wrong with these p and q. It's not violating any conditions of a simplified radical. As a matter of fact, it's great because I have a pq right here. So this is going to be pq. And don't forget these indexes of 3. I always do that. So I'm going to try and be better here. Put my indexes where they belong. And now I can actually subtract these. It's not going to look very pretty, but it's going to be pq squared minus 4. And then it's going to be, in parentheses, the cube root of pq. And then that's it. So it felt like if we didn't have this p here, we have a difference of squares there, which I could probably factor a little more. But this p is stopping me from factoring anymore here. But yeah, that is it. So I just combined this and that on the outside in parentheses, and then your cube root of pq is going to come along for that. Whew, look at these. So let's take a look. We'll do this as hopefully as painlessly as possible and see where it takes us. So what I'm going to do is I'm going to simplify this fraction. It looks like it could be simplified. So this is going to be 2, and then square root of both of these are divisible by 4. So this is going to be 8 and 9, which is pretty sweet because I can take the square root of 9. So this is going to be 2, and then the square root of 8 simplifies to be 2 radical 2. Again, that's from that Pythagorean theorem business that we have been stressing, and this will be 3 right there. So let's take a look at this one now and see where this takes us. So 27 and 108, I'm hoping that that is divisible. Let's take a look. Heck yeah. So this is going to be 2, and the square root of 27 and the square root of 108 is going to just be the square root of 1/4, which will just be 2 radical 2, 3 plus 2 over 2 1/2. Sorry, because again, square root of 1 is 1, square root of 4 is 2. Again, what I did was I simplified these 27 and 108. 27 divided by 27 is 1. 108 divided by 27 is 4. And last but not least here, the only way that we can go ahead and actually add these together is if you have a common denominator. So we could do that if we really wanted to. I don't really want to, but I will if I have to. So you know what, let's just do it. So let's do 2 plus 2, which is of course going to be 4. And then what I'm going to do is I'm going to get the common denominator of 6. So this is going to be, again, all I'm going to do now is focus on the fractional part. So this is going to be 4 radical 2 over 6 plus 3 over 6. And when you add these, again, just the fractional part together, there's not a whole lot going on with the numerator, since again, you don't have the same radical, same index. Matter of fact, this doesn't even have a radical there. So this is going to be 4, and then plus this will be 4 radical 2 plus 3 over 6. So this is just not very friendly, not very cool to do. This was kind of a mean problem for them, and I will do my best to not give you something like this on the test. All right, moving right along, multiplying and dividing radical expressions. So let's do maybe a couple of these, and then I'll pause the lecture for now, and I'll post another video tomorrow, and we'll finish up chapter 7 and maybe dabble into chapter 8, depending on if I'm in the mood. All right. Okie dokie. So remember, when multiplying these, you don't have the same restrictions. As long as you have the same index, you can combine the radicands. So just like before, we can distribute this radical 11. If we had a 7 out here, that's what we would do. So we're not going to stop that process just because we have a radical 11 out there. So this is going to be 5 radical 11, because 5 times radical 11 is just 5 times radical 11, minus the square root of 11 times the square root of 2 is going to be the square root of 22. And you just want to double check the fact that you have any perfect square factors here. You don't, because 2 and 11 are both prime. So there's not going to be any perfect square factors there. So this is the final answer here. The next thing that you want to do is go ahead and distribute this in. Usually what I do before I dive into distributing 7, which is my initial reaction, at least when I first look at this, I go, oh, I'm going to have to use the distributive property. But then I looked inside real quick, and I saw that we have perfect square factors lurking inside of these radicands. So we need to take care of that. You don't have to do it right away, but you probably should. All right. So we are going to take care of the perfect square factors of 54 and 24. So the perfect square factor of 54 that I care about is 27, right? Nope, not a perfect square. Sorry, not a perfect square. That is a perfect cube. I'm back in the cube mode over here. But this is going to be 9, because 9 times 6 is 54. So this will simplify to be 3 radical 6, because remember, the square root of 9 is 3. So I'm going to start to sort of skip that like trivial step to break it up to the square root of 9 times the square root of 6 to get 3 radical 6. I'm going to start skipping that step since we've done quite a few of those already. And then over here, perfect square factor of 24 that I care about is 4. because 4 times 6 is going to be 24. So remember, the square root of 4 is 2, and then we get the square root of 6. And what's cool about this is that this is adding and subtracting radicals. As a matter of fact, we have the same index with the same radicand, so we can just combine these to get 1 radical 6, or just radical 6. So you don't even need to use the distributive property here, because this is just 7 times one of these radicals. It's not 2 of them anymore because we were able to combine them. So the final answer here is going to be 7 radical 6, and that's all she wrote. All right, you would still end up with the same exact answer here had you distributed your 7 into both of these and then went through the motion of simplifying these radicals. But I found that the path of least resistance here is definitely to simplify the radicals first, see if you can shake it down a little bit, and then if you can, great. If not, you're going to be distributing the 7, right? Okie dokie. So this is, we'll probably just stop with this slide. Things get a little hairy here with these. So this is where my box method really comes in handy when you're starting to multiply these radicals. I find it to be the most organized way to multiply these radical expressions, okay? So I'm going to go ahead and do this instead of using the FOIL method. Sorry, book, I'm not following your directions. You'll get over it. So we've got 2 and then radical 3, and you've got 1 and radical 5. So now you just do the multiplication just like you would if this were an algebraic expression. So 1 times 2 is 2. 1 times the square root of 3 is the square root of 3. 2 times the square root of 5 is 2 square roots of 5. And the square root of 5 times the square root of 3 is the square root of 15. So this gives you everything that you need. All the components, everything's positive, so I don't have to worry about signs or anything like that. So everything is positive, positive. And there's nothing here that you can combine. So your final answer is just going to be this: 2 plus the square root of 3 plus 2 radical 5 plus the square root of 15, which doesn't matter what order you put this in. I will not be picky. It is what it is. So just do what you can with this. Put it in whatever order you want, and even MyMathLab will not care what order you put it in either. Okay. So let's do B, and then we can call this a video for tonight. The first thing that I noticed with B is that this is a difference of 2 squares. I see it right away because I've trained my brain to recognize that I have it when I see it. So I hope that this will still kind of shake out to be what I need it to be. All right, so let's take a quick stab at this problem. Again, using the box method, and then I will show you how to use the shortcut, and that will definitely save you later on in the class when we start using the conjugate when we're rationalizing the denominator. So bear with me. So again, this is a positive one, this is my negative one, so make sure you keep track of that negative because it's going to be here. So 4 times 4 is 16. 4 times radical 5 is 4 radical 5. 4 times negative radical 5 is going to be negative 4 radical 5. So you can see immediately these will cancel each other out. You can do it now or later, it doesn't matter. And then this is going to be negative square root of 5 times positive square root of 5, which is going to be negative square root of 25, which is just negative 5, right? And again, if you need to see that out, it is negative square root of 25. The square root of 25 is 5, which is just the negative 5. And then last but not least, you just have these to combine, which is pretty sweet. So our final answer here is just 11. All right, 16 minus 5 is 11. Pretty cool. Remember, there's a shortcut. The shortcut to this says, if you recognize that you have this difference of squares, it is x squared minus y squared. So what does that mean? It means you can get your answer pretty darn fast if you take the first value and square it, so 4 squared, and subtract the second value squared. And you'll see, again, hopefully right away, that this square root and this square cancel each other out, which leaves you with 16 minus 5, which is just 11. Know this shortcut. Please, if you have a difference of squares, which you will have later in this class, not today, in the next video, when we start dealing with the conjugate, you are going to really want to make friends with this shortcut so that way you don't have to multiply them out every single time. Okay? So this is a good place to stop for now, and we will pick up where we left off with these last couple of problems here, and then proceed. All right, so I hope that this was helpful for you. Thanks for tuning in, and enjoy the rest of your day or night whenever you're watching this.